Hi guys, so this next unit is about acids and bases, which are more specific ways to classify compounds that we've already studied. So let's start off with the Arrhenius theory. Arrhenius studied acids and bases and he studied their properties, and he came up with these definitions or the reasons why acid compounds have the properties they have and base compounds have the properties they have. So he said if something is an acid, it releases H plus, which is the hydrogen ion, in solution. So what does that mean? I will give you an example of an acid. So HCl is one of our very common acids. If you think about this, guys, HCl, these are both nonmetals, so they're bonded by covalent bonds. Molecular compounds, when they dissolve in water, they're not supposed to break up into ions, but acids break this rule. When you dissolve acids in water, they do break apart into ions, unlike other covalently bonded things. So this is going to break up into H plus and Cl minus. So what's happening is as I dissolve HCl in water, I'm increasing the amount of hydrogen ions present in that solution. So I'm making the solution more acidic. We could actually see this written this way too, HCl plus water. Instead of the hydrogen ion kind of floating around alone, what it'll do is it'll attach itself to a water molecule. So instead of H2O, we'll have these H3O ions in solution. And if you remember from your polyatomic ion unit, these are called hydronium ions. So whether we're talking about hydrogen or hydronium, if you have a lot of them in your solution, you're going to have an acidic solution. Okay. Easy way to determine if something is an acid by looking at it. They usually start with the letter H, like HCl. Okay. If something is a base, Arrhenius said it releases hydroxide ions in solution. So bases follow the rule. Bases are a metal, usually, plus the hydroxide ion. So here's an example, NaOH. Ionic things are supposed to break up into ions when we dissolve in water. So sodium hydroxide would break up into sodium plus the hydroxide ion. So by dissolving sodium hydroxide in water, you're increasing the hydroxide ion concentration in the solution, which is going to give the solution basic properties. So let's scroll down to this table. This is a nice list that gives you the general properties for acids and bases. As far as conductivity goes, both acids and bases are electrolytes because they both break up into ions when we dissolve them in water. So as far as that being a useful property for telling an acid apart from a base, that's not going to help because they have that in common. pH is different. We're going to spend a lot of time on the pH scale in a couple videos from now, but if you can just remember that acids have a low pH, below 7, and bases have a high pH above 7, then that's good for telling them apart. As far as taste goes, they taste different. Acids taste sour, bases taste bitter. Sour, I think of biting into a lemon. Bitter, I think of biting into dark chocolate. Okay, people get them confused, but they are different tastes, and you should never, ever, ever taste in the lab to tell them apart. Indicators, we're going to spend a lot of time on indicators, but for now, indicators are things that change color, and the color indicates a pH range for you. So the two that you guys should really commit to memory are litmus paper and phenolphthalein. Litmus paper, you can dip into a solution, and if it turns red, it's an acid, and if it turns blue, it's a base. Phenolphthalein is a liquid. And if you drop it into an acid, it stays clear. And if you drop it into a base, it turns pink. So there are a lot of other indicators, but these two are really good for differentiating between acid and base. As far as their reactions go, they react with different things. Acids are corrosive, so they react with most metals. If you pour acid on metal, the metal will start dissolving and you'll see bubbling. You'll see hydrogen gas being made. Where bases are they're caustic. So they won't dissolve the metal, but they'll kind of make it feel slippery. If you get base on your skin, it kind of feels cold and slippery. So it kind of isn't as in your face, like scary, I guess. If you drop acid on your skin, you'll automatically start to feel it burn a little bit and you'll get a little red and irritated. Soap is an example of a base. So I'm not saying that anything that's an acid or a base is dangerous. It is if it's concentrated enough, I guess, or has a high or low enough pH. But just to give you an example of what they would feel like. Okay, as far as neutralization goes, they react with each other. If you react an acid with a base, they'll make a neutral solution. If you react a base with an acid, they'll make a neutral solution. So that's something, again, they have in common. Now, looking at this list, ammonia, NH3, has everything on the base side, except it doesn't fit this Arrhenius definition. It's not ionic. It doesn't have a hydroxide ion in it. So what would make it have all these properties if it doesn't follow that definition? Bronsted-Lowry came along and they came up with a second rule or a second definition for what's an acid and what's a base. As far as like multiple choice goes, if they don't call out their names, you'll see it referred to as like, oh, one other theory or an alternate theory. And you want to think, oh, I have to memorize a second definition. That's bad. So bad is going to help you understand this definition. The B stands for bases. A stands for accept. The other A stands for acids. And the D stands for donate. And we're talking about accepting and donating hydrogen ions or protons. Either one is okay to say. So the hydroxide ion is non-existent in this definition. So what do we do? When you're given an entire reaction, you have to figure out which one is accepting H's and which one is donating H's. So think about you donating clothes. You're only able to donate clothes because you have extra clothes. You have enough clothes, so you're able to give some away. We're going to think about that the same way here, except with H's. So let's start with the first thing in the reaction. I see an H, a C, and an O in this ion. On the other side of the arrow, what other compound has similar elements in it? This does. So you want to have a pair, one from each side of the reaction. Now you want to think, okay, of these two things that I just underlined, which one has more H's in it? The HCO3 has more H's in it. Because it has more H's, it's going to be able to donate an H. It's going to be able to give one away. So what kind of things donate? Acids donate. So of these two that I underlined, this is my acid, and this has to be my base. My next two things also have elements in common. They both have H, P, and O in them. Which one has more H's? This one. So that must be my acid. It's going to be able to donate, meaning the other thing is my base. Okay, let's do one more together. HCO3. What has the same thing on the other side? H2CO3. Which one has more H's? Then that must be my acid. Here we go, HPO, HBO. Which one has more H's? This guy. So this must be my acid. Okay. So how does this model expand on Arrhenius's concept of an acid or a base? So look at HCO3 in both reactions. In the first reaction, it's an acid, and in the second one, it's a base. So you can have the same substance, I'll say, acting as both. In one reaction, it's an acid, in the other one, it's a base. So depending on what it's with, it can either accept or donate a hydrogen ion. Also, guys, water. A lot of times water is included in these Bronsted-Lowry reactions, and that's the most common answer for give me an example of a neutral substance. Everyone knows that water is neither an acid or a base, right? Sometimes in the Bronsted-Lowry reactions, water can give away one of its H's or it can accept an H. So water can act as an acid or a base. And that totally goes against Arrhenius's definition. Okay? All right, so as a last question, guys, I'm going to have you complete this Bronsted-Lowry reaction labeling what are the acids and what are the bases in both the forward and reverse reaction, and we will talk about this tomorrow.